Okay, welcome to the talk Apache Spark. What's new in version 2.4. So, first of all, let me introduce myself. I work for the IBM Center for Open Source Data and AI Technologies in San Francisco. We have two remote workers, one is in Switzerland, that's me, and one is in South Africa. And we are currently contributing to 10 open source projects, and we have 7 Apache contributors and more than 100 contributors. And you see here we are active contributors to Apache Spark. Formerly the center was called the Apache Spark Technology Center, and we are now contributed to Kubeflow. I will tell you something about the Kubeflow later. So if you want to check out more about me, I also post always my slides, my recordings of these sessions on YouTube and GitHub. So that's the link. Maybe I should find a shorter one. And who of you is familiar with Apache Spark? Okay, 50%. So I'll give you a short intro to Apache Spark. So we have the JVM process, and the JVM process on a single node, of course, can't scale. So you have limitations in main memory and CPU resources. And therefore, the idea is to distribute the JVM processes on different nodes. So the idea is you have an executor JVM, and usually you have multiple per node. And the rule of thumb is usually around the number of cores or hyperthreads you have in the machine. Then, of course, you can distribute those executor JVMs on different machines that need to get a cluster. So we have solved the main memory problem, and we have solved the CPU core problem, and now the data problem is solved nowadays by just attaching some sort of object store or cloud object store attached to a switching circuit as fast network connection, and usually that works unless you have very I/O bound workloads, which is not the case anymore. In most of the cases, then you can still go back to something like HDFS, where you partition the file and you get the virtual file which spans the cluster boundaries. So in Spark, the central data type is an RDD, a resilient distributed data set. It's a distributed immutable collection of data, and it can be backed by files, or object store, or databases, or NoSQL databases. It's mainly in memory. Unless you load it from a persistent storage, then it's kept there, and only the parts which you are needing are loaded into memory. And the other way around, if you write to your RDD and it doesn't fit into memory, it gets automatically stripped to disk. And it's lazy, what I already said, only if you need the data is loaded from the persistent storage. So the idea is it's iteratively parallel, so it doesn't matter whether you are using it on top of 1 kilobyte or 1 petabyte, the code always stays the same. So you have a couple of supported programming languages, Java, Scala, Python, and R. They differ a bit. So Spark itself is written entirely in Scala. But therefore it can easily be used from Java, although Java is not a data science language. And then you have R, which is the data science programming language, which has been the data science programming language, but currently Python and PyData is getting more and more traction. So sometimes only a subset of the APIs are available, so you have to be careful a bit. Python, on the other hand, is getting more and more traction. Here I feel it can get slow, but this problem is solved now in most of the cases, unless you are directly working on the RDD API and using Lambda notations. We'll let you later. So here a little overview. Again, the slides are on my GitHub, so you can always refer to it. So who of you is in functional programming? Who could explain how functional programming works? That's maybe 15%, 30%. Okay. So it's based on the mathematical concept of Lambda Calculus. So its first implementation I found is Lisp. So Haskell is something I had learned during studies. Of course, quite hard but very interesting. Scala is the most recent representative, but we had a nice talk after noon, somebody using functional programming on top of Java. So luckily I think there's a recording of that session, so I can check it out later. Scala supports the whole principles, but also Python, R, and Java have rudimentary support, and for us that's sufficient here. So the idea is you have a function that's plus citizen in functional programming. In this case, you have a function which just increments the value by 1. Then you have data, that's a list, and the idea is to send the function to the data which gets applied on the data, and the result is then another list which has incremented each value. So the difference is that you don't loop through the data, you just send the function to the data. That's the layman's terms maybe. So if you are implementing it like this, then parallelization becomes easy because you just partition your data and you send the function to each partition, and since they are not dependent on each other, those operations are now running 3 times in parallel. That's the heart how Apache Spark achieves parallelism. But since this is a bit complicated, nobody really likes to implement stuff in functional programming besides some nerds, because it's a much more cleaner way to implement things, but it's also a bit more complicated. Therefore, there's a wrapper around the RDB. So the RDB is a functional API, but there's a data frame, and data scientists, they log data frames. So they behave like tables. And you have data frames in R, you have data frames in Python pandas, therefore it makes sense to have data frames in Spark as well. On the data frame you have a data frame API, it's more or less a relational API, so you have functions you find in SQL as well. And therefore, besides the API you have a pure SQL interface which supports all the queries in ANSI SQL 2003 standard, which is pretty cool. So it also supports access to a JDBC driver. Of course, you can write, but you can read. Okay, also all selects and aggregates pure SQL supported. There's another type which is called data set, which is specific to Java and Scala. It's a typed data frame basically. It gives some % more performance because of the static typing. So again, schemas are supported on the RDB as well, but on data frames it's mandatory. So they have a schema, you have column names and column types. They can be inferred from the data or also explicitly defined. And therefore you have 2 optimizers. One is called the catalyst. The catalyst is something you have in relational databases as well, which actually analyzes a query and then creates a physical execution plan which has been optimized based on statistics of your data set. So it's database functionality here, it's pretty cool. And the other one is the project Tungsten, which actually mitigates some drawbacks of the JVM, for example, garbage collection, and also object representation. So in original Java, you need 48 bytes for a 4-byte string, because all the management code takes a bit of space, and also the garbage collector is relatively good at object lifetime estimation, but Apache Spark knows it better. So therefore, the project Tungsten uses the unmanaged version, so it doesn't keep management itself. Okay? There's also a cache-friendly data structure and also code generation in Project Tungsten. So that's 2 very important components of Apache Spark since version 2, I think, or 1.6 or something. Then we have here Spark 2.4, and on the right-hand side I have a list of all the Spark issues in the Jira tracker. So basically you can just read all those and then you can skip my talk, or you just listen to me. I've just cherry-picked a couple of those. Of course I cannot cover all, but I've covered those which I think are most interesting. And I think that most interesting is barrier execution. So Spark is a de facto standard for open source data integration now. So many companies are using it in production, including Apple. So that is an unofficial news, someone told me. And also eBay, that's official, and another set of huge companies are using it, including major banks. So it's definitely something which is robust and stable, and also I think the most active and the largest Apache project, and one of the largest open source projects ever. So it's definitely a really big thing. The execution model in Spark is suitable for data transformation workloads, but not so for machine learning workloads. And barrier execution basically adds that. So let's have a look at the notions of job and task in Spark. So a job is a composite of different tasks, and usually you have at least one task per data partition running in parallel or in sequence, which we'll see in a second. So as we have seen, the order doesn't matter in data transformation. So the order when the tasks are executed on a particular job. And also, they do not need to run simultaneously. So you see task 1, 2, and 4 are terminating before task 6 and 7 are running. Okay, that's perfectly fine in data transformation. But so since you have here this property that you are just sending functions to the partition of the data. Also, if a task fails in that paradigm, then it's not a problem. You just restart it and it just goes on. Okay, and even it might complete at the same time, since here task 7 still is scheduled later. But neural network training is different. So this is the way how a neural network is trained in parallel. You use the same neural network and you put it to different compute nodes, and you also partition your data, and you train a neural network, and every now and then, so in neural network training terms, this is called an epoch or a batch or a mini batch. All the learned parameters of the neural network are sent to a central parameter server, and then just the average is taken, and that average is then sent back. So for those who are familiar with machine learning or deep learning, the model has an architecture and then a set of weight parameters. And those weight parameters are learned during training. And here, these weight parameters are learned in parallel. And therefore, since they are trained with different partitions of the data, the weights are diverging. But since you then synchronize them and take the average, they can every now and then they are synchronized. Okay? So it's actually working quite well. The only catch is that you have a central server, which is a single point of failure and introduces some bottlenecks. So the newest version of this is the so-called reduce all paradigm, where you just have a ring and you average the data you have, you send it to the next one, the next node adds his values and makes the average of the rest and so on, and that passes through a ring. It's much more stable. So basically you have those two ways of doing it, and it depends also on the hardware and topology which one you are using. So now you have a problem because all those tasks need to communicate with each other, so they must run at the same time. Okay, this is also not a problem since now the Spark version 2.4 has this barrier execution mode. So every now and then, again, the weights are stored. I've indicated that with this little database, and then the next batch or epoch or mini batch is started. That means if now the task is failing, the whole job number 2 has to be restarted. But still this is fine since we are checkpointing every batch. So what we do is we just copy the weight values which we have already learned from job 1 to the end of job 2. We create a job 2a, which basically starts from scratch. And if that successfully succeeds, so if it terminates successfully, then we can start job 3. Okay, that's barrier execution. One other thing which has to be solved, so that actually allows to use TensorFlow and PyTorch and all those frameworks in a PySpark context. I haven't seen implementation, so this is pretty new. We are still waiting for an implementation, but something else needs to be prepared for this to work properly, because now if we create, for example, a pandas data frame out of a Spark data frame, all the data is copied from the persistent storage to the JVM heap and from the JVM heap to the Python heap. Okay, that's something we don't want. Therefore, we have another Spark feature request, which has been implemented this year in version 2.4. That's using stream-based access using the Apache Arrow library. That's actually working like this. So Apache Arrow addresses exactly that problem, that if you switch and swap between the frameworks, you always have to copy and convert the data. But Apache Arrow allows for an in-memory representation. That representation is shared between all the frameworks. So that means the format is always the same in memory, and also you can just use a pointer, and that's called zero copy reads. So if you have a data frame in Spark, the in-memory representation is the same as you have in the Parquet file, which you have read. And also, if you then create a pandas data frame from the Spark data frame, which is backed by a Parquet file, everything is just pointers, so nothing has to be moved. Okay, and actually it supports the column store, so also the Parquet file is a column store. That's a much faster way of accessing data usually, and that means PySpark doesn't need to have a copy in its own heap, and that means also TensorFlow doesn't need to have a copy of data in its own heap. But it's not 100% solved, because if you want to put the data into TensorFlow, you need to pass it as a NumPy array into a TensorFlow data object. And once you convert the pandas data frame into a NumPy array, all the data is read. So I have currently a request open here, and I just need to waiting for some feedback on that, but it's ongoing. Then another hype is Spark on Kubernetes. Kubernetes is a total hype everywhere, even I've heard in CERN they're using it. Do you have the time by chance? My watch is on my cell phone.
It's 8 past 5.
Okay, that means I have another 12 minutes. Yeah. Okay, so Spark on Kubernetes is something you need to have, because Kubernetes is everywhere. And one thing which is already there since version 2.3 is that you can just run Spark submit against the Kubernetes cluster. So it supports the Kubernetes API, and it generates pods for you containing the Spark driver and the Spark workers. So whenever you run a job against a Kubernetes cluster, a driver pod and some worker pods are generated, the job is executed, and after it has been executed, the pods are destroyed. Therefore, you also need to make sure that your data is read and written to some persistent external storage. So that's how such a command looks like. You see here, you don't need to run pip control here, it's just based on a Spark submit. Another already existing technology to run Spark jobs on Kubernetes outside of Apache Spark is Kubeflow. It's just for your reference. You see here, Kubeflow is pretty neat because each of that nodes in this graph can be backed by a different technology. So you can have one node using Apache Spark cluster, another node using some scikit-learn, or another one using PyTorch or whatever. So you can build and compose such workflows on framework boundaries, and also the communication between different nodes here is through files on an object store. Okay, just that you have seen that once. So, but those two technologies are not interactive. So we want to have something interactive, and until Spark 2.3, even IBM has been using the Jupyter Enterprise Gateway, which was developed by my center, and this allows to have a proxy. So the gateway is a proxy, and the proxy communicates to the Jupyter system and also to the Kubernetes cluster, and dynamically allocates resources in the Kubernetes cluster. That's pretty cool. We are even using that here in our cloud tooling. What's the studio? You see here, this is a notebook. I'm reading a data frame, and all the stuff behind is on Kubernetes, and in a drop down you can select the number of CPUs and GPUs you want to implement. Something dynamic. So that's the way it was, but there's now another kid on the block, or another option since version 4. That's the client mode. The client mode actually allows that the Spark driver runs outside the Kubernetes cluster or in the pod you have defined, and that of course allows for interactive shells and Jupyter notebooks, so only the workers are then automatically provisioned, and that's the same behavior like we have in the Jupyter Enterprise Gateway. Then we have eager mode, so everybody's talking about eager mode. Today morning in my TensorFlow talk, I also mentioned in TensorFlow 2x we have the eager mode, line by line execution, and that's now also available in Spark. So previously, if you use Spark from Jupyter Notebook and you have executed something which returns a data frame, that's the string representation of the data frame which has been used. But now the _ref_underscore method has been implemented on the data frame. Therefore, Jupyter can call this method and it gets you an eager representation on your data. So whenever you are executing something which returns a data frame object, Jupyter automatically shows you the head on the first rows. That's available out of the box. In Spark 2.4, you just have to set the Spark Jupyter eager enable to true here in the Spark session definition. Then I have some outcomes. So two important, you have seen that it's a huge list, but two important things which will go into Spark 3.0. First of all is the standardization of the data exchange between Spark and the third-party Python deep learning and machine learning frameworks, which is an ongoing process. I told you it's not really clear how you go from a pandas data frame, for example, to a TensorFlow record or TensorFlow dataset. And the other thing which is also important is the accelerator-aware task scheduling. That means Spark will know. So Kubernetes already knows how many GPUs are attached to each worker node and can appropriately schedule and place the pods. But Spark can't so far, and this is something coming to Spark version 3. Yeah, that was maybe a fast but important overview about the new features. Again, if you are interested, buy my books, and also if you're interested, take my courses. So the first two are on Apache Spark, the third is on TensorFlow and deep learning, and also you can get 1 month for free if you take that challenge, or you just take it in audit mode and you get it completely for free. Okay. Yeah, so we have 7 minutes for questions, additions, and complaints.